presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. This show is funded by supporters on Patreon and Subscribestar. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Now, good morning, everybody. I hope everyone's having a wonderful day. I want to welcome you to another fun session of Big O Bootcamp. So, hope you're having a wonderful day. And I'm not going to get started quite yet. I just want to see how everybody's doing today and just get a follow-up for where we were last time. So, for those that are watching right now live, welcome on in. And of course, everybody is welcome. So if you have a friend that's out there that wants to learn more about algorithm analysis, computer science, and all of that fun, just come on down. Anybody here is welcome, okay? But anyways, seeing as this is Big O Bootcamp, I got to wear the hat. That's sort of just how this goes. So I got to make sure I put the hat on. Got to make sure I put it on properly, because otherwise I sort of clip myself, which is kind of funny. But no, please everyone's having a good day. I have the chat just on over here, and I got TTS enabled. So if you type, say if you're on Twitch, for example, you can type there and I can hear it audibly. Keep in mind, put your questions in the chat, discuss, have fun. If there's a fun crack a joke you want to make, go for it. It's all happy to have that on here. And of course, I have it collecting pooling from Facebook, YouTube, and Twitch. So whether you're on any one of these platforms, I'll see it here on the chat. So if you have any questions during the examples I'm going through, the concepts that I'm teaching here, I will be happy to talk about those things here. But yeah, no, hope you're having a wonderful day. So sorry, I'm just getting really excited here because I get to talk about something that usually I would argue that a lot of CS classes, especially that do algorithm analysis, don't have time to go into all the nitty-gritty details for. And you might find some of these concepts kind of interesting if you've never heard of them before. I usually like to cover them a little bit, but there's only so much time often in these kind of classes. So before I get back to where I was last time, and keep in mind I'm going to keep the chat open on the screen and all that for anybody that's coming on in. What I'm going to do here, and first, hopefully my audio is okay. Let me know. Let me know. I should maybe double check that. Okay, I think we're okay. Okay. I got the thumbs up. So, anyways, what I thought I would do before I get... Okay, no, wonderful. So anyways, what I'm going to do before I get into the main topic today, I'm just going to remind you what the definition of Big O is, the formal definition that we'll be using. And I'll be talking about how this is going to work into what we're going to focus on today. So if you weren't here last time, that's okay. I'm going to just give a little recap to where we were. And then once I'm done doing this, I'm going to be moving into the stuff that I want to focus on today, okay? So that's why I'm keeping the chat and everything open, because in case anybody's dropping on in, just because I just got started here. So I just want to remind you of a couple quick things before we get into all the juicy bits today. Because what the plan is today is I'm going to cover a concept called smoothness. But before that, I'm going to do a warm-up exercise, just showing you how I can use this definition of Big O. So that I'll be focusing in on, and I'll be attaching it to something I talked about last day. So I'm just going to go through the definition, and then I'll start on our first example here in a moment. So anyways, just to remind you the definition of Big O. So suppose I give you two complexity functions, f and g. So typically, just as noted previously, a complexity function is defined where the input is typically a positive integer. So when I give it to the function, I give you a positive integer, it spits out a non-negative real number. So that means it could be 0, which most algorithms will not have it where it spits out 0. In fact, it would be kind of strange if you actually think about it, that the number of operations that an algorithm performs would be 0 for some reason. It's conceptually useful when, say, you have it where some part of your algorithm isn't actually ever executed. This is why sometimes having this here is helpful. That's one of the reasons. And also, I had some other discussion about what you can rely or relax a little bit here. And that's okay. There's a lot of different variations. But this is the most common one in algorithms analysis you'll run into. Often people will even restrict this even further. But that's okay. It's okay. The same ideas here will still apply. So suppose I give you two complexity functions f and g. We say that f is big O of g, which I must stress from last time, I may write this in a couple of different ways. For example, I may use the set theoretic in. So this means in. But you could read this as is as well. Likewise, there's also this conventional use of the equal sign, but I must stress it does not mean equals. It still means is. And we had this discussion last day. So another thing to keep in mind is that when I say f, then, well, f, so remember, I'm talking about this function f. I usually write out what the input is that follows it. So keep in mind the context I use it. For example, here I'm talking about a function f. I'm just describing its input. It's a shorthand and an abuse of notation. It's a very common one in the juicy M word, that mathy stuff. But at the same time, I also will use it in the sense when I compare, say, have it inside of inequalities, for example. In that sense, I'm literally talking about the output of the function. So f is big O of g, if and only if. So just as a reminder for those that aren't as familiar with this phrase, if and only if. It means that what I write here, if this is true, whatever follows this has to be true. If this is false, meaning f is not big O of g, then whatever I'm going to write after this also has to not be true. If and only if there exists c, which is going to be a positive real number constant, and n0, which is a positive integer, such that for all n greater or equal to n0, the following inequality has to hold. And it must hold, like I said, for all n greater or equal to n0. It has to be that f of n is less than or equal to c times g of n. So reminder, that is the definition of big O that we'll be using. It's a very common one in computer science circles. This will be the one I'll be appealing to almost every time. Now, that being said, does anyone have any questions about the definition of big O, or are we doing pretty good so far? So I went into a lot more detail about this definition, and we did some examples with it last time. So if you find yourself wanting to say, hey, Dan, can I talk to you about all of this fun stuff? Can I see some simpler examples? I got you covered. There's lots of examples I've went through, and those are actually coming out on the channel as well. So I thought I would do another example. So I'm going to switch back over here. So let me just get that there for now. And must stress that if there's any questions, and it's really something I can't just address on the fly, I'll address it when we get there. As in, when I conclude the example, I will most certainly do that if it needs to be a lot more technical. Okay, everybody? So, anyways, today we're going to be starting off with our first example. So let's consider the following example. So what I want to do is, here's our first example, just as a little bit of a warm-up here today. Last time I went through things like polynomials. We talked a little bit about, we'd seen actually some interesting examples, but I thought I would show you something that actually kind of connects nicely, say if you need other kinds of exponents for your big O result. So for all integers k greater or equal to 0, and suppose I give you a real constant, epsilon. So you can think of epsilon as any real constant that is greater than 0. So this means it can be very small. It could be like 0.1. It could be like 1. It could be 10,000. Whatever you like, as long as it's some real number that's bigger than 0. But it's a constant here. Then we're going to say, so the claim that we're going to prove is that n to the power of k is big O of n to the power of k plus epsilon. Now you might ask, Dan, why would I need this information? Well, like you'd be like, oh, well, look, it's clear, it's obvious to me. I'm just using these words deliberately to talk about, okay, reasoning here. Okay, it's obvious that this k is not it's not going to dominate over, I'm just using kind of loose terminology here, over k plus epsilon because epsilon's greater than 0. That's true, right? But the thing is, we need to actually have some way to check this. And I'll give you an interesting application of this claim in a moment. So let's prove this claim. And it's actually surprisingly simple. Remember, we come back to our game plan. We're going to figure out those two constants, right? Because that's what's in the definition, right? It says we have to find these two constants, c and n0. We have to find them, but I also have to reason out like why they work, right? I can't just give them to you and just say, oh yeah, just deal with it. They just exist. If I'm doing a formal proof, that isn't sufficient. So I'm going to say we find constants. Constant c. So remember, c is a positive real number. And n0, which is a positive integer. So that for all n greater or equal to n0, it has to be, well, I'm just going to plug in my two functions. Remember, this is f, that's g here, so that's f, n to the k, and n to the k plus epsilon is g. So it means that n to the k is less than or equal to c times n to the k plus epsilon. Now, we're going to use that approach that we had last day. I called it the lookalike approach. And you'll notice very quickly that we have n to the k on that one side, on the left-hand side. To mimic this on the right-hand side, notice that k is in fact present in the exponent and epsilon is in fact greater than 0. So we're going to use that intuition we talked about where we said it was kind of obvious. So we're going to just use that intuition to help us. But we need to pin it down, okay? So notice that if I just make c1, then it's n to the power k is less or equal to n to the power k plus a little bit in the exponent. So if we go with that, it seems pretty nice. So I'm just going to make an observation first before I pick it, and then everything will flow a lot nicer, okay? For all n greater or equal to 1, observe that when we divide both sides of the inequality, both sides of the inequality, we're talking about this one right here, by n to the power of k, we get the following. And keep in mind, this is a legal step, so let's just proceed. Well, it says that n to the power of k divided by n to the power of k is less than or equal to c times n to the power of k plus epsilon over n to the power of k. Well, if you look at this right-hand side, if you remember properties of exponents, and keep in mind, I will do at some point some coverage of this, is that if you have n to the power k plus epsilon divided by n to the power k, notice the bases of these exponents are the same. So it's actually, instead of it being where, like, if you just look at this, like, okay, what do we do with that? We subtract the exponent. So I have k plus epsilon subtracting k, and it means I end up with just epsilon. So I end up with c times n to the epsilon, which if I rewrite this inequality now, this is actually me saying, because remember, n to the power k divided by n to the power k, this is just 1, right? So we have c times n to the power of epsilon is greater or equal to 1. So you can see quite quickly once I've done this, or at least my hope is is that we just need to now figure out the constant. Well, the great thing about this is that we're going to pull out a property that we know about n to the power of epsilon. It's a polynomial, but it isn't necessary that it has an integral exponent, meaning it's not integer valued. It may be real valued, as we have epsilon being a real number. But remember, epsilon is positive. We're going to pick c is equal to 1. Then we need to find n0 so that n to the power of epsilon is greater or equal to 1 for all n greater or equal to n0. Well, here's the great part. Well, if you look at n to the, if you have a background in calculus, you'd look if you look at n to the epsilon, you would know right away, if you calculate the derivative of n to the power of epsilon, you could see that this, in fact, the derivative of n to the epsilon, it will be something that is strictly positive. And if you know this fact, then you know the function is increasing. It's an increasing function. So that means that if I plug in, say, n is equal to 1, notice I have 1 to the epsilon. Well, 1 to the epsilon, well, 1 to the anything that where the exponent is greater than 0, it's just 1, right? So that means that if it's an increasing function and 1 to the epsilon is equal to 1, that means that, well, that means that it's never going to get smaller than 1 on that this right-hand side is always going to be bounded. So notice I have c to the n to the epsilon. Well, if this is going to be increasing, so n to the epsilon is always going to be increasing regardless of what epsilon is. And I know that when I put in 1, so it means if I go 2 to the epsilon, 3 to the epsilon, I know it's always going to be the case that it's going to be, this function's value is going to increase, okay? So we're going to use that fact to help us conclude this proof, okay? So observe that n to the epsilon is greater or equal to 1 for all n greater or equal to 1. Now, if you need more explanation here, you just say that n to the epsilon is an increasing function and 1 to the epsilon is equal to 1. So I would recommend, if you need more detail, I would suggest strongly you put that right here. In my notes, in fact, I make a note of this. But I'm sort of running out of space here. So select n0's. Oh man. Select n0 is equal to 1. Then now we could just conclude, because now we can just use the definition of big O. Therefore, by the definition of big O, then we could say n to the power of k is big O of n to the power of k plus epsilon. And that concludes the proof. I'm just going to write that box there to say that we're done the proof. So this is a really nice, cute proof. It just relies on the assumptions of an exponent. But I wanted to tell you one interesting fact that comes out of this, is that last day we've seen how we can prove properties for polynomials where the exponent is an integer. So suppose I gave you something like this, like n squared plus n plus 5. Last day I showed you how you can easily prove, like it's like a cookbook approach. I showed you how you could prove that this is big O of n squared. Now, you can see very quickly that if I were to know how to do it like this, and suppose I gave you another function. Say it didn't look like this, but say it had real exponents. Like say it's like n to the power 2.5. Okay. Well, the technique I gave you, well, you can't really, the way the argument works is a little different. It would not work the same way as the proof did before, except now you would have to just accommodate for the fact that, like, oh yeah, now you're allowed to have halves and so on. But my point is that you know how to prove things like this, but suppose I wanted to know, as a matter of fact, that suppose that I wanted to claim to you that this is also big O of n to the power of, say, 2.01. Suppose I had some other part of an algorithm's running time and it ran in n to the power of 2.01. Well, here's the neat part. You could take the complexity function from that, add it to this, and you would end up with something like that. But suppose that I didn't necessarily know that this part was big O of n to the power of 2.01. Well, here's the neat part. If I know this is big O of n squared, and I know that n squared is big O of n to the power of 2.01, the big O has a very nice property called the transitive property. Big O is transitive, has a transitivity property. So it's what we call transitive. So if you know this fact, and you know this fact, then what you can conclude is that function is actually big O of n to the power of 2.01. This comes from the transitive property. I'll be talking about this transitive property and its proof in another session. So, are there any questions about this example? Nice to see some lovely faces in the chat. Let me just get back up. There we go. I see you, Tor. But no, hopefully everyone's having a good day. That's why I wanted to do a little bit of a warm-up in case anybody wanted to stop by to say hi or wanted to come in and just chat about stuff. But yeah, no. So this is just a cute... so if ever you need to like increment the exponent by some real value, and keep in mind that this still is like... It generalizes over several different things at the same time. If you look at this carefully, for example, when you make k 0... you'll notice that this is just 1. And then it's saying that this is big O of 1 to the power of epsilon, right? There's several other things you can also say here, right? And remember, epsilon is just quite literally, like you could make it any positive real number. And that includes integers too. So this is also another way you can also argue that n to the power, like say if I give you n to the power of 1, this could be n to the power of 1 plus epsilon, and epsilon could be whatever you want it to be. So if you want to show that n is big O of n cubed, you could use the same proof right here. So this is another way you could do that, and it also gives you basically a cookbook for doing that as well. But it's a very cute proof. It's just, all it is just using the properties of exponents. It's really basic. But it's really nice once you figure it out. So when somebody talks to you and says, Dan, that's just obvious, and they ask you for a proof, here's one way you could do it. So that being said, hopefully everybody's having a good day. So I want to switch over to start talking about the main topic here. So I'm going to erase this board here, now that we've done a little bit of a warm-up here. Because we're going to be seeing a concept that honestly I wish more computer science students got to see. Because oftentimes it's just this thing that just sort of just happens, and students don't really know why you can do it. It's just sort of something that some CS profs will just throw at you, and then they just expect you to know it, but sometimes I find that a lot of those students have never learned it. And it's often a technique that makes things a lot easier to do for your analysis. So oftentimes, if you know that your algorithm's going to have a running time that has a certain behavior, if you're looking at your algorithm and you're like, okay, it seems like it behaves this specific way. And if you have to deal with issues of, say, rounding numbers, or the numbers just don't cleanly divide each other. You sent me something. On Messenger. I'll have to see it afterwards. But now what was it? The big thing is that that very often you haven't, just like actually the session, like our last session, I showed you actually an example where I had shown you that the nth harmonic number is big O of log n. And I had to do a bunch of bookkeeping to make that proof work. So for example, I had to determine another number that is always like the rounded up version of our number to the next highest power of 2. And then I worked with that number as a bound. Now, I would like to be able to cut all of that out to make it as much simpler of an analysis as I can. Very often you can use this technique, for example, to simplify analyses, for example, for things like binary search, algorithms that, for example, use, say, cutting, like such as divide and conquer algorithms, very much where they subdivide the problems into chunks. You'll find that the analyses, the way they work out is they often require you to like, oh, I have to half it, or I break it into 3 parts or 4 parts. And sometimes those don't have, actually, they're not divisible by each other perfectly, meaning that it doesn't cleanly divide the instances into appropriate sizes that are all of equal size, making your analysis a lot trickier to do, at least if you want to do it properly. So what I'm going to be doing here is I'm going to be showing you that there's actually a shortcut, a way that you can cut corners, but here's the great part. Cutting corners is great when it actually works, and it always works. And we won't want to have situations where cutting corners leads us to make mistakes. That is unacceptable in this area. I will. So let's get in on this, okay? So today our main focus is going to be this concept called smoothness. And as I was so anyways, we're going to talk about this idea called smoothness. So I find very often, like I was saying previously, that in a lot of CS circles, especially among students that learn analysis of algorithms, this topic is often glossed over. So I very often like to go into a bit more detail here, and you'll find that I'm showing you a lot of things that you may or may not have seen before. If you've seen it before, that's wonderful. If you've never seen it before, that's also wonderful, because you're going to be here to enjoy it here with me today. So let's get in on this. So before I can talk about smoothness, I have to talk about a concept about functions. And I may have brought this up previously. If not, one thing I need to talk about is the concept of an asymptotically non-decreasing function. So if I give you a function and I say it's asymptotically non-decreasing, which many functions have this property, especially the ones that we talked about studying last time. Many of them will have this property. So what is this? So if I give you a complexity function, so it's a complexity function is called asymptotically non-decreasing. Asymptotically non-decreasing if there exists n0 so that for all n greater or equal to n0, that f of n is less than or equal to f of n plus 1. So let me draw you a few pictures just to give this idea across. So let me draw a few pictures here. So just to make sure you understand the idea. So the big thing here is that there's going to exist a point where whenever I put in the input, it's always going to be that the next highest input is going to be going to, so if I have this input, and I check if it's less than or equal to this other input, then it must be that when I apply the function to each, it has to be that the output of the function for that given input is less or equal to the output of the function given the next input on integers here. So let me just give you a picture of what I'm talking about. So suppose I have, here's 3 different functions. So I got f, suppose I have f, g, and h. These are 3 different functions, and each of them, suppose I'm increasing its input n. So there's a lot of examples of asymptotically non-decreasing functions. So I'm just going to draw out some examples here. I mean, it seems something kind of like this last day. So notice here that this function, as an example, is the case. It is something we call a non-decreasing function. Notice that the function, whenever I put my, let me get my sticks out. Whenever I get my sticks out, I'm coming, I'm coming. So notice that if I look at this function, whenever I compare it against the next input, notice that it only goes up or becomes flat when I plot it out. It only goes up or it goes flat. Meaning, if you plot it out, at least if we're talking about a function of this sort where it only has one input like this, it will go up or it will remain flat. So this is an example of what we would call a non-decreasing function. This right here, notice that the input, whenever I look at this function g, notice that the input always goes, so whenever I increase the input, the output always goes up. It never goes flat. This is an example of an increasing function. Here, however, notice that this one has a little bit of a stranger behavior, right? Notice that it goes up, it can come back down, but notice after this point right here and anywhere after this, notice that it goes up and it may even go flat. So the first example is of a function called a non-decreasing function. G is an example of an increasing function. And the third one is actually an example of an asymptotically non-decreasing function. So this one's non-decreasing. This one's an increasing function. We actually talked a little bit about that a moment ago. And this is an example of an asymptotically non-decreasing function. Some people call it an eventually non-decreasing function. It's the same exact thing. Asymptotically non-decreasing. But here's the thing. Here's the catch. That all of these are asymptotically non-decreasing. Believe it or not, all of them are. So if you just apply this definition, you look at this, say, okay, well, that there exists some point so that f of n is less than or equal to f of n plus 1. Well, look. I could just put n0 right here. So look, n0 is right here. And if I compare the input versus this next one, every time it either goes up or it remains flat, which is what this means. So it goes up or it remains flat. Notice that I could just pick n0 to be right here. I don't know, it's some integer. Say it's 1 in this case. That would be perfectly fine. Because imagine this is a parabola, for example. Then notice it only goes up after this point, never goes flat. But notice here that if I find out that n0 is right here, presuming the behavior of this function always goes up or remains flat after this, then notice that if I just care about what's happening after this point, this is also asymptotically non-decreasing, as I said just previously. But all of these are asymptotically non-decreasing. Does everybody see that? So it means that when you talk about non-decreasing, increasing functions, and asymptotically non-decreasing functions, all of these, including these other two categories, these are all asymptotically non-decreasing, meaning that we're talking about a large family of functions, especially, and that also will include all the functions that we've talked about up to this point. So this includes, so as examples, you can talk about, say, for example, a constant function, logarithmic functions are asymptotically non-decreasing, polynomials, a polynomial, or exponential, for example. So the kind of functions we talked about before, these are all cases where you may find asymptotically non-decreasing functions. So that means that many of the functions that you're talking about when we talk about algorithm analysis, all are asymptotically non-decreasing. This is a helpful thing to know about. So all I'm going to do is I'm going to presume that all of these examples I gave you are shown to be asymptotically non-decreasing. And the way that you can do that is that you can, of course, for example, identify this n0 in a similar manner. It's not exactly the same. Most certainly, it's a somewhat different game plan. You would figure out what this n0 is, and then what you have to do is check that for all n greater or equal to n0, this inequality works. So that's the game plan. It's a little different. There's a lot of different analytical techniques for doing that, and I'm not going to focus so much on that here. That may get some treatment sometime in the future. But I hope that this is clear enough to you that all of these functions would be asymptotically non-decreasing. So that brings me to really where we're going with this, because we're not quite out of the gate when it comes to terminology, but most certainly we're in the scope of what I want to talk about. So there's certain functions, and similar to many of these, not all of these, but many of these, it'll be the case that the behavior of them is what we would call smooth, meaning that if I take sampling of the input, so if I take some parts of the input and I plot that out, and I look at the asymptotic behavior only for those inputs, it means that it actually can generalize over all the inputs. So in particular, there's a certain pattern or simplifying assumption that I can make where I can take a look at it, and the shape of the function is such that the differences between the samples I make, just as an example, versus the actual overall function, they are going to be similar enough by some constant amount. So that's kind of where we're going with this. So many functions are what we would call smooth. So you can use this fact in algorithm analysis to simplify the analysis you're performing for your algorithm. So that means that you can you can actually just, instead of looking at like every input n when you're doing your time complexity analysis, you can restrict the input just to, say, powers of 2 or powers of 3 or powers of 4. For example, if you've learned about things like divide and conquer algorithms, you may actually have some familiarity with this idea if you've ever heard of something called the master theorem. The same kind of underlying theory is sitting underneath that. So what I would like to be able to do is I would like to know, or at least analyze algorithms, or suppose I get the complexity function, suppose that's f here. I want to be able to show you that f is big O of g, but so suppose that I want to have the ability, because say, for example, like I was mentioning a little earlier, suppose that it's really hard or it gets really ugly to do the analysis for all inputs n, because say the numbers don't cleanly divide each other. Say, as a common example, it might be something like your favorite case of like merge sort or binary search, where, for example, the input may not cleanly divide into 2 equal parts. It may be the case that it may be like the ceiling or the floor of halves. I would like to be able to have it where, for example, I can make presumptions, so I can restrict or simplify what n is. For example, the one that I'll focus on here is when n is a power of b. And this is some fixed integer constant for us. So what I'm saying is that it would be that n is equal to b to the power of k for any k greater or equal to 0. So what I would like to be able to do is, under such a simplification, I want to be able, and like I said, this is the good kind of cutting corners, because what I'm going to show you is that you can make this simplification and you can still end up with the overall result that you want to desire, even if you're only analyzing this for this specific set of inputs. What I want to be able to do is show, if I have this, I want to give you some condition. So there's some stuff in here that relates to this idea of smoothness, such that I could just simply say that f is big O of g unconditionally. So what you could do is you could do your analysis with the smaller restricted inputs, so like n is a power of 2 or n is a power of 3 or something like that. and I want to be able to do this with some conditions in place, I can automatically get as a result that f is big O of g without ever having to actually go and consider all the inputs, because all of the heavy lifting is done by this concept of smoothness. So there's going to be some condition, which we're going to talk about, that's going to give us this ability to go from the simplified analysis. So very often you'll run into this when you're doing algorithm analysis. Sometimes people say, well, assume n is assume without loss of generality that n is a power of 2, for example. It's very common that happens. Now, they may not necessarily be using smoothness, but this is one vehicle for allowing you to do such things without losing any generality, because the smoothness of the functions allows it to happen. That's not the only reason why somebody can get away with that. For example, the analysis itself could be simple enough that you can easily just simply have it where whatever their analysis is doing is always accounting for more, say if you were to cleave it up or down, for example, if you're breaking the halves. I just want to make the remark that sometimes it's unclear if they're using smoothness or not. But I just want to make it clear that yes, you can get away with some neat things using this idea of smoothness. But I just wanted to tell you that this like secret little trick that some computer scientists are using when they do time complexity analysis or different kind of analyses, is smoothness allows you to kind of smooth out these issues. But I'm saying that it isn't the only way you can do things like this. That's what I'm saying, is that there's just some condition in here that allows you to do this. We're going to talk about one of those. I hope that is clear, everybody. So, that being said, let's talk about what the heck is all of this about. So, I'm going to define something called smooth. And I must stress that it does technically have also a stronger definition based on what we call big theta notation, but I'm not talking about that here. So a complexity function. So if I want to talk about a smooth function in this context, I'll say a complexity function f that is both, so it has to be both these things. It has to be both. The first thing is that it's asymptotically non-decreasing, which we've just already talked about. And two, it has to be that the following is the case. And this is why in Big O Bootcamp, why we'd be interested in this, is that f of 2n is big O of f of n. So, but the second condition is saying is that if you look at the input, so whenever I give you an input n, if you multiply that by 2 inside of the function, so whatever the input is twice that, it has to be that this is big O of f. So I'm going to do some examples with you to illustrate the idea of smoothness, what a smooth function is. So I'm just going to need another marker here. So as I said, all the functions we're going to study here are asymptotically non-decreasing, just to be clear. So I'm not going to focus so much on that here. I'm just relying on your understanding of how these different functions we talked about work. So I thought I would do a couple examples to really warm us up to this idea. So for example, I told you, so if we talk briefly about constant functions, you can actually show that constant functions are smooth. So constant functions. So suppose I give you f, n is equal to d, where d is just some positive integer constant. So what we're going to do, so we already talked about how these are asymptotically non-decreasing, so I'm not going to focus on 1. Instead, I'm going to focus on 2, that second condition. So what we're going to do is I'm going to walk you through the process of proving using the definition of big O, the second condition. So as usual, we have the game plan. I tell you what I'm going to do with our proof, okay? So we find constants. C, which is a positive real number. And N0, which is a positive integer, right? Such that for all n greater or equal to N0, it has to be, remember, our goal is to show that f of 2n is going to be less than or equal to c times f of n. So I'm just going to plug that in here just to write it out directly for you. But I'll write its equivalent counterpart here. So f of 2n is less than or equal to c times f of n, which this, for our case, we're going to be talking about d is less than or equal to c times d. Well, this should remind you a lot of the very first example we did last time. So notice that it's just, we're playing lookalike again. So notice that, wait, no. It isn't just this, right? Notice it isn't just this. Or is it? It's 2 times n. But notice that n doesn't appear anywhere in the function. So yeah, it is that d is less than or equal to c times d. So remember, whatever is the input, you would write 2 times that for wherever n appears in the function's computation, right? But notice that here is just some constant. So 2 times the input doesn't make any difference. It's still d. So this makes it easy for us. So I'm just going to pick c is equal to 1. And normally here I would say that, oh, we're going to find n0, but notice that it's a constant function. There's not very much interesting going on here. So then notice that both sides of the inequality are equal, right? Both sides of the inequality. That U is looking a little bit spicy, I guess. It's got a little hook on it. Somebody let them know about having a good day, okay? Both sides of the inequality are equal for all n are equal to 1. So that means you just choose n0 is equal to 1, and then you're done. And now we just have to invoke the definition of big O, and we're piece of cake, right? Therefore, by the definition of big O, D is big O of D, right? And function f of n is equal to D is smooth. And we're done. Because remember, we already know about the first condition. That's okay. That's okay. So I thought this would be helpful to get an idea of what I'm doing here. So it's just another big O claim. That's all it is. So I'm going to do, let's do 2 more examples. Just I want to make sure it's very clear how this works. It's a little it's a slight tweak of what we were doing last time. So here's another example. Let's prove that log base 2 of 2n, so I'm just going to put the second condition right here. I'm going to show you that this is big O of log base 2 of n. So remember, this is the second condition if I want to show that log base 2 of n is smooth. So we already established, we already know that logarithms are, in fact, increasing functions. So log base 2 of n is an increasing function. It always goes up. It just slowly grows. But it indeed goes up if you plot it out. So that indeed makes it an event asymptotically non-decreasing. So if I prove this property right here, that means that log base 2 of n is smooth. So let's write out a proof for this. So walk through the same process. Let us find constants. Constants c, which is a positive real number, and n0, which is a positive integer, so that log base 2 of 2n is less than or equal to c times log base 2 of n for all n greater or equal to n0. Just give me one moment. I'm just going to grab another marker. It seems like I have a sort of playing Russian roulette with the markers at this stage, but let me just fling this off. It's gone. It's gone. Just get some more markers here. Okay, here we go. So, this is the game plan that we have, and I would like to show you that, remember, the goal is to show that log base 2 of 2n is big O of log n. So, I just have to find these two constants, right? That's the goal. So, you might say, Dan, what are you going to do to make this happen? Now, here's something that's neat. Now, you may or may not know this about logarithms, but when you have a product inside of a logarithmic function like this, there's something you can do to that input. Notice that it's 2 times n. Does anybody know what I can do to that logarithm there? Any tips on or tricks that anybody is aware of that maybe we could do with that logarithm right there? So I'll tell you that there's a property that logarithms have over products like this. If you're unsure about what I'm referring to, just try writing out what logarithm means, like what's the definition of a logarithm, in terms of writing it like exponents. So if I have a product inside there, this is the same as me doing something. So I'll start writing it, and if you have any ideas, just let me know. Notice that by the product rule of logarithms, or product law. Oh yeah, this marker is much better. Product rule of logarithms, which I'll remind you of in a moment. We could say the following. So watch this. Watch this. So remember, we're dealing with this inequality right over here. So let's write on over here what we could do with this. So here's what we could do. So watch this. Well, remember we have on the left-hand side log base 2 of 2n. Well, log base 2 of 2n. Well, this is just equal to log base 2 of 2 plus log base 2 of n, right? So you could distribute products inside of logarithms over addition. But what's log base 2 of 2? Well, let's think about it. 2 to the power of what is equal to 2? 1 plus log base 2 of n. But this, notice that, remember, we talked about what an increasing function is, right? Well, for what values is 1 going to be bounded from above, or I guess technically you'd be allowed to be equal to it, to be log base 2 of n? Well, I'm going to do the following. I'd used this trick last time. I'm going to replace 1 with log base 2 of n, plus another log base 2 of n. And I'm allowed to do this because log base 2 of n is greater or equal to 1 for all n greater or equal to 2. And this is because logarithms are increasing functions. So just don't forget that fact. So don't just blindly think about this. Remember, we're working under the prism that we understand that logarithms are increasing functions. So this is the reason why I can do this. But this is just equal to 2 times log base 2 of n. But this, remember, this all is true for all n greater or equal to 2. So just keep that in mind. So when I wrote this out over here, I should say for all n greater or equal to 2. So, now what am I going to do now? Well, let's think about it. This is just, well, look, if I make c is equal to 2, so I'll say by picking, c is equal to 2, and n0 is equal to 2, the above inequality is satisfied, right? Because that's what we get right here is the right-hand side of such the inequality, which is the same as the one I had in the previous sentence. Therefore, by the definition of big O, log base 2 of 2n is big O of log base 2 of n. And we're done. So we just used that one property of logarithms to make this work. So are there any questions about this? Yeah, this one seems pretty slick. If you understand that one property about logarithms, we're pretty good. So I thought next I would do one more example, just illustrating the second property of what a smooth function is. I'm going to show you that a polynomial of the form n to the power of k is also smooth. So one thing I do want to stress as I'm going through this, like I said, the definition of a smooth function can be defined in terms of big theta, which is something I have not discussed here. But I must stress that the game plan is very similar. It's just that you need to understand within that prism. But anything you can say about big theta also has to be true for big O. So that's why we're sticking with big O here. So let's do another example. Let's prove that 2n to the power of k is big O of n to the power of k for any constant k greater or equal to 0. So if we can prove this, and remember, we know that polynomials like of this form are asymptotically non-decreasing, this would mean that polynomials of this form are also smooth. So here's the proof. So we're just going to walk through the same process again. So to prove the claim, we find constants. We find constant c, which is a positive real number, and n0, which is a positive integer. So that for all n greater or equal to n0, 2n to the power of k is less than or equal to c times n to the power of k. Now here's where it gets a little fun. Now, this is where sometimes it's actually really important to know the difference between a variable and like a constant. So we have names for these different variables, but some of them are allowed to vary. Some are fixed. They are constants, such as k. K is a constant. 2 is a constant, right? Well, what I'm going to do is I'm going to make a constant, and at first you're going to be like, Dan, what are you going to do to make this work? Because it's 2n together raised to the power of k, and then I have c times n to the power of k. Well, watch this. Sorry, I'm getting very excited about this. Well, I'm going to make a really big constant, okay? Well, because remember, k can be really big. This is a claim involving any constant k. So I must stress that if k is big, this is also going to be a big constant. I didn't say that all of these constants end up being nice and simple. Like, they're very easy to write down, but they might actually be pretty big. This constant is going to make this proof go a lot smoother. So I'm going to pick C to be 2 to the power of k. You might say, Dan, why would you do that? It's because I'm going to make something that looks similar to the left-hand side. Remember, I'm just playing lookalike. So now we would find, so I would normally write right here that we're going to find some n zeros such that that inequality is true. But I'm going to use the following property of exponents. By the power of a product property. Now, for those that are not acquainted to this property, it works like this. So I'll just write it off to the side here. What it says is that AB to the power of m is equal to a to the m, b to the m. That's what it says. So what I'm doing is I'm applying the exponent to each separate thing it's being multiplied by. So I could just simply use this, right? So by the power of a product property, which I'm going to stress, remember, like I said, it's this. All I have to do is now do this. And you're going to notice it's going to be a lot smoother. Pun intended, okay? Notice that both sides of the equal, both sides of the inequality to n to the power of k, and all I'm just going to do is I'm going to apply that property, which, remember, this will just end up being the right-hand side to the power of k times n to the power of k for all n greater or equal to 1 are equal. So now all I have to do, well, I already know what n0 should be. It should be 1, right? So choose n0 is equal to 1. Therefore 2n to the power of k is big O of n to the power of k. And we're done. So with this proof, now you know that polynomials, so if I could show you this involving n to the power of k, then you know it's smooth. So if you have a complexity function, it gets categorized by big O of n to the power of k, you could say that n to the power of k is smooth. This will be a very lovely property for us to have at our disposal. But I must stress that not every function is smooth, just to be very clear. So I should say that not every function is smooth. So just as an example, suppose I give you f, where it's going to be 2 to the power of n is not smooth. So if you want to see why this is the case, in my notes I'm going to have the proof for this. It's a contradiction proof. Remember the game plan when we show big O claims, we find those two constants, right? Well, the way this would work is that you show me that these two constants can't exist. So yeah, so not every function is going to be smooth. We've seen that constants, logarithmic functions, polynomials are all smooth. And these are very common ones you'll run into when you're doing time complexity analysis. Which is nice. That's wonderful. So all the main ones that you've seen, and there's other ones too, like n log n is also smooth. Most of the ones that you're familiar with are smooth, but some of them, like I said, if you try sampling their points, for, say, by a multiplicative constant like this, you'll see that the gap is going to be too wide, such as with an exponential function. But I'm not going to get too much into the intuition around that. But now we've seen some properties that we can have when it comes to, like, okay, we know what a smooth function is. I'm going to need some more terminology to make this work. So now you know about the idea of a smooth function. You know what a smooth function is. We know how to prove a function is smooth. I'm going to need some more machinery to make this work. But I thought before I get too into the nitty-gritties of the weeds of all this stuff, I thought it'd be a good idea. I'm just going to show you what the end goal is here, okay? We'll come to the actual proof for this, but I want to make sure you are aware of what we're trying to aim for. And it's going to be akin to the same thing we talked about just earlier. So this is what we're going, so this is our goal here. So this is going to be the goal that we're going to try to reach. So let there be complexity functions f and g. So I suppose I have these two functions. So suppose that I had the following right here. Suppose I have f is big O of g, but it's the case that n is a power of an integer constant. B greater or equal to 2. So suppose that I showed you that f is big O of g with this restriction on the input. I must stress that there's other restrictions you may have, but this is the one that is specific for the proof that I'm going to be showing you. There's other ones that exist. I have an example in the notes. For example, if you want to have it where n is a multiplicative constant of b, there is other ways you can characterize this. So for example, if you want to make sure that n is always even or something, you can do things like that. But I'm going to focus on this one because it's a very common form for algorithms that take on the divide and conquer pattern, or the paradigm of divide and conquer. So here's the condition that makes this work. So remember how I told you that there's some condition that I can use to go from this to just this. So I want to be able to just say f is big O of g without having to say that n is some specific inputs. So here's the condition that I'm going to be getting to. So this is what I would like to show, is that if you have this in place, then you can automatically go from here to there, and this is actually what we're going to call the smoothness rule. So what I'm going to be trying to do is proving this thing called the smoothness rule. That's the goal. So presuming that f is asymptotically non-decreasing, so I've defined this already. Asymptotic. It's always, all right. I was wondering why it's a little bit funny here. Asymptotic, there we go, is asymptotically non-decreasing. And it has to be, so f is asymptotically non-decreasing. That's all you need for it to work. And g is smooth. So as long as you have these two things in place, so if you have this and you have this, so f is asymptotically non-decreasing and the g is smooth, which remember, g meaning it's smooth means it's asymptotically non-decreasing. And as we've seen before, that f of 2n is big O of n. So big O of f of n, sorry, f of n. If we have these two properties, then we can go from here to there. You don't have to do any other work than just invoking this smoothness rule, as long as you know that you have these two properties. So this is a very nice shortcut for your analysis. And I got to show you how you go from here to there. That's my goal. So this is what we call the smoothness rule. So my goal here is I'm going to prove to you the smoothness rule. But to do this, I need some more machinery to make that work. That dreaded M word, that mayonnaise, mustard, or whatever it is. Miss Kitty, I'm not quite sure. So we're going to need some more terminology to make this work, for at least this setup. There's other ways you can prove different kinds of smoothness rules, but this is going to be the one we're going to focus on. So let's lay out some more things for us. So you might say, Dan, you gave us a definition for smooth, that f of, remember, f has to be asymptotically non-decreasing, and it has to be the f of 2n is big O of f of n. But I need another concept that's going to generalize over the idea of smooth. So the first thing I need to tell you is that being a smooth function actually generalizes to an even stronger condition. So that's going to be the first claim I'm going to have here. So we're going to define something called be smooth. You know, be smooth. Be smooth today, guys. So at first, this is going to look like it's a generalization of the idea of smooth, but I'm actually going to prove to you that any function that is smooth is be smooth. So this is just, so we say a complexity function, function f, that is both, so you're going to see that this definition is just like the smooth definition with a small wrinkle. It's both, 1, asymptotically non-decreasing, and it has to be that f of bn is big O of f of n. And this has to be for every integer constant b greater or equal to 2. So just keep in mind that the b is within the input of the function. So it's b times n here. It's just like we had for our smooth function, it was just 2n. I'm saying it's bn. The b is not a multiplicative factor here. It's inside, which makes it look a little bit stranger than what we might be used to. So this is going to be, so what the next claim we're going to prove is going to be a vital ingredient for proving the smoothness rule. So here's a theorem. So hopefully you can follow along with me on this one. And it's going to be using something called mathematical induction. So I might need to get some help in a little bit from our lovely furry friends. So if a complexity function f is smooth, then f is be smooth. So that's the claim. So if you give me a smooth function, it has to be smooth. So we're going to start this proof up, okay? There's going to be some moving parts to this, so you have to make sure you follow this very carefully. So what we're going to do is we're going to make use of mathematical induction, the principle of mathematical induction. So I'm going to give you an idea of how this proof will get laid out. And it's going to use the principle of mathematical induction to work. So I'll give you an idea of how this will get set up with the induction in a moment. So I'm just going to start off by denoting what exactly we're going to prove. For any integer b greater or equal to 2, let b of b, so capital B of lowercase b, denote the statement b of b, where f of bn is big O of f of n. So I'm going to presume that the function f is smooth. So our goal is if f is smooth, then it has to be that this is true for each value of b. So technically I could have said if f is smooth, then this, but the setup of this proof is pretty darn straightforward. So I'm going to start off by trying to show this for a small value for b. So I'm going to start off with step b is equal to 2. So what I'm going to first do is I'm going to show you this, what we're going to call the base step. And then I'll give you the idea of how induction works, and I'm going to get some help from Miss Kitty. So remember that if I have b is equal to 2, notice that that's just the definition. This is just saying it's smooth, right? So we don't have to do anything. Since f is smooth, f of 2n is big O of f of n, right? Proving b of 2, right? It's pretty darn straightforward. I don't like using those phrases, but it is a tautology, right? So we know f is smooth, and we're given literally the second condition of what makes a smooth function. So this brings me to the part where it really matters, where we have to start being a bit more careful about how we carry out mathematical induction. So I'm going to need some help from my lovely assistant here, Miss Kitty. She might be a little bit pissed off. So let me just grab Miss Kitty here. Come on, Miss Kitty. Here we go. We got Miss Kitty. So Miss Kitty's going to help me teach us how we would carry out this mathematical induction proof. Everybody say hi to Miss Kitty. Hello. There's Miss Kitty. Yeah, she looks a little grumpy here at the moment. At least I think. She might be in a pleasant mood. I'm not quite sure. Oh, she just woke up from a nap. Okay. That would explain everything. She's looking a little sleepy here. So what we're going to do is to teach us mathematical induction. We started off with b is equal to 2. I would like to show this for all b is greater or equal to 2. So I know how to do it for the first rung of the statement. So I want to imagine it like I'm trying to teach Miss Kitty how to climb up a ladder to the top of the bunk bed to get back to her nap, okay? So I have b is equal to 2, so I know how to get Miss Kitty up one rung. I need to show how I could give you an arbitrary rung of this ladder for any one of these values of b, how to go from b of 2, for example, to go to b of 3, to go from b of 3 to b of 4, to b of 4 to b of 5. So I'm going to use induction based on any one rung, and I'm going to show you how to get to the next rung so I can show Miss Kitty how to climb any one arbitrary rung in the ladder. And then by doing that, we'll be able to show Miss Kitty how to get back up to her bed to have her nap. Does that sound okay, Miss Kitty? I think she agrees. So Miss Kitty was very thankful for you to help us out. I don't know if you want to hang out, but I'm going to do now the induction step, Miss Kitty, okay? So thank you so much, Miss Kitty. Thank you for all your help. I'll let you get back to your nap, okay? Okay, here you go, Miss Kitty. There we go. Everybody give thanks for Miss Kitty. Miss Kitty is helping us learn about mathematical induction here and how we're going to use it. So let's go to the actual induction part of this proof. So we know how to do it. We know how to prove the statement for b is equal to 2. So the idea in mathematical induction is I would like to show you if I know if the previous statement is true, so for example, b of 2 is true, how can I use that to prove b of 3 is true? And if I have b of 3, then most certainly I can show you how b of 4 is true. Almost like I'm lining up dominoes, or in this case, helping Miss Kitty climb up a ladder by showing you teaching her how to climb up one rung in the ladder. So if you have that, then you could start at b of 2, go b of 3, b of 4, and you can show how to go up any one rung in the ladder and help Miss Kitty get to her napping spot, okay? So let's do the induction step. So we're going to be proving that b of k, if b of k is true, then b of k plus 1 has to follow from it. So we're going to fix some k greater or equal to 2. I usually use a different variable for this as opposed to lowercase b, because I want to be able to fix this value of k and be able to play around with it for an arbitrary k. This is in contrast to the way I parameterize b over there, but in most senses, a lot of people won't make any delineation between these two things. That's okay. I just like to be a bit more precise about how I formulate the induction step. And I'm going to assume what we call the induction hypothesis or the inductive hypothesis. This is just the previous rung in the ladder. So this is the one that Miss Kitty's going to put her foot on to get up to the next rung. And assume that B of K, or F of Kn, is big O of F of N. So this is what we call the induction hypothesis. And I would like to be able to, I'm going to presume this because if I have, say, if I want to prove that B of 3 is true, then I'm going to presume that B of 2 is true because I already showed you B of 2 is true. So the idea is I'm going to show you from any one previous rung how to get to the next one. But the idea is I must use the previous statement to help me get there. That's at least the way I'm using the induction here. So I'm going to presume that this holds. There's a lot of ways this could go wrong if you do not set this up properly. So if you're misusing induction, this is how you set up the induction here. You can't just assume any one of them is true without an appropriate setup here. You have to be careful because we're going to invoke the principle of mathematical induction at the end. So it has to be that one follows from the next. So just watch carefully how I do this. So we will show that B of K plus 1, which this is saying F of K plus 1 times N is big O of F of N. That's what B of K plus 1 says. We will show that B of K plus 1 also holds. So that's what we're going to be trying to do. If we could do this, then we can use the principle of mathematical induction and complete our claim. That F, if it's smooth, then it has to be B smooth. So remember that because F is a smooth function, it has to be asymptotically non-decreasing. So I'm going to use that fact. So I'm going to say function F asymptotically non-decreasing. So for sufficiently large n, and I must stress that you could give this a name. I'm not going to here, but I'll just give it, I'm just going to use it in the appropriate way so that I'm just trying to make this a little easier for us so we don't have to make more names for variables. But the asymptotic non-decreasing function definition says that there's a sufficiently large n, which we called in that definition n0, large n, that f of k plus 1 times n is less than or equal to f of 2kn. So this is a claim I'm going to make, is that f is asymptotically non-decreasing. So if there's a sufficiently large value of n such that if I put in the input k plus 1 times n, it's going to be that it's less than or equal to f of 2 times k times n. So watch how I get this. Because remember, it's asymptotically non-decreasing. Remember, the shape of the function will be that it goes up or it gets flat. So watch this. So I'm just going to look at their inputs because that's what an asymptotic non-decreasing function allows me to do. Since k plus 1, remember that's this right here. Remember, it's k plus 1 times n, 2k times n, right? So I'm just going to look at the k plus 1 and the 2k. Sorry, yeah. It's less or equal to 2k, which this is no different than me writing that 2k minus k plus 1 is greater or equal to 0, which this is no different than me writing k minus 1 is greater or equal to 0. So since this is the case, since this is true for all k greater or equal to 2, right? So this has to be true, like this statement right here has to be true for all k's greater or equal to 2, which is all you need, right? because remember, the statement involves b being greater or equal to 2. So that's all you need here to make this work. So I'm just looking at the input. So the idea here is that if I have this bound in place, then I should be able to massage this in terms of big O. So this is how we're going to use this. So watch this carefully. So I'm just going to use the smoothness of f to do the following very crafty step here because of this property. Then, by the smoothness of f, because remember f is smooth, we get the following. So let me just finish up the proof over here. We're almost done. So there's a very slick step that's going to happen. It's due to the big O notation. And there's a reason why I wanted that 2 there. So watch this. Because remember, our definition of smooth had this 2 in there, right? It was 2 times the input is big O of the function, which is the thing itself, right? So we're going to use that. So then by the smoothness of f, we get the following. F of k plus 1 times n is less than or equal to f of 2kn, which this is equal to, I'm just going to rewrite it in a way that's a little bit easier for you to see what's going to happen, is 2 times kn. But I'm putting the kn together and I'm multiplying it by 2. But here's the thing. If I have the function, and suppose this is the input of that function, what can I say about this in terms of big O? Well, because f is smooth, I can drop the 2. So I have f of kn. And yes, I will not read that out loud, okay? F of kn. I'm not going to try to abridge that description. But what does this mean? That implies that there's actually those 2 constants that are going to exist for the definition of big O to work, right? Implying the existence of constants. This is why I just needed to be sufficiently large for the value of n. Because at the end of the day, if I get this right here, then I could just tell you that these constants exist. This is why I didn't introduce another name, because I was just going to have some more, that's just some bookkeeping that isn't going to matter much at the end. Implying the existence of constants. C1, which is going to be a positive real constant, and N1, which is going to be a positive integer, such that for all n greater or equal to n1, that's important, it's not n0, I haven't talked about n0 yet, n1, that it has to be that f of k plus 1 times n, all in the input there, is less than or equal to c1 times f of kn. That step's a very clever little step here, but this is what we need to get our key ingredient for the induction step. Why? Well, if you look at this very carefully, you actually can see that I actually have we have something that looks like our induction hypothesis, or the inductive hypothesis. It's just sitting right here, right? It looks eerily similar to this, right? So that's what I'm going to do, is I'm going to use this fact. So by the induction hypothesis, so I'm going to show you how you take a statement involving b of k, and I'm going to show you how you show that b of k plus 1 also holds, presuming that b of k holds. By the induction hypothesis, f of kn is big O of f of n, right? So there are constants C2 which is a positive real number, and n2, which is going to be a positive integer, where it has to be that f of kn is less than or equal to c2 times f of n for all n greater or equal to n2. So this is rather interesting. So notice that I have something that says f of kn, and I have something that says f of kn, and I also have f of n right here. Notice that I would like to bridge this to connect it up with this. If I could connect those two together, we're done. So I'm going to use a little bit of bounding tricks here to find an appropriate constant for c to complete our proof. So now I have this and this to play around with. So watch this. By selecting constants, so I'm going to pick c to be c1 times c2. This is a very common trick for proving big O identities. c1 times c2, and I'm going to make n0 be the maximum, the larger of the two of n1 and n2. The reason why is because I would like to make use of these two inequalities here. So if I make n0 big enough that it subsumes both of them, meaning that both these have to be true, then we're okay. I can use them if I make n0 big enough. Then, notice here, so watch this, watch this. Okay. So I have f of kn is less than or equal to, so remember we have this over here, right? So we have f of k plus 1 times n. That's less or equal to c1 times f of kn. Well, you would agree with me that f of kn is less or equal to c2 times f of n. So most certainly what I could do is put this inequality, just like put this right here. Like just try, okay, so I know this is going to need a c1 right here to make this work. So I multiply both sides of this by c1. And then I could put this right here. Then f of k plus 1 times n is less than or equal to c1 times f of kn, right? Which this is less than or equal to c1 times c2 times f of n. But this is right here c, right? So that's equal to c times f of n. And this holds for all n greater or equal to n0. But what is this statement? This statement is b of k plus 1, right? We've proven b of k plus 1. Which proves b of k plus 1, completing the induction step. Now, I could use the principle of mathematical induction and we're done. Therefore, by the principle of mathematical induction, I'm just going to abbreviate it as PMI. B of B is true for all b greater or equal to 2, which proves the claim, and we're done. So are there any questions about that? So this is the first key ingredient for proving the smoothness rule, is that we show that every smooth function, so if a function is smooth, then it has to follow that it is B smooth. We're going to need this B smoothness property for what we would like to prove next. So one thing I can mention is that you can actually simplify this proof a little further. If you analyze the proof for the transitive property of the one I talked about earlier on in this session, which I will show you that proof at some point. It'll be somewhere out there. If you have that, you'll notice actually it's buried in this proof right about here. So you can actually simplify this proof by invoking the transitive property of big O. That big O is transitive. It's transitivity of big O. So now we know that, so the big recap for where we are is we know all smooth functions, they are B smooth. So if I give you a smooth function, you could say it's B smooth. And now we could prove the smoothness rule. So let's now do that. So now we have the key ingredient. Isn't that exciting? So we've actually characterized smooth functions using a much more general property, which is kind of interesting in its own right? It shows you that the simple definition of being smooth characterizes actually quite a bit. It's actually a really nice, simple definition, which I think is kind of surprising the first time I seen it. So just to recap where we are, so we're going to prove the smoothest rule next. So we're going to prove the smoothest rule. So remember, we have two complexity functions, f and g. So let there be two complexity functions. F and G, where F is big O of G, when n is a power, n is a power of an integer constant, integer constant b greater or equal to 2. So remember the characterization that we need for the smoothest rule is as follows. If f is asymptotically non-decreasing, it's asymptotically non-decreasing, and g is smooth, then it has to be unconditionally that f is big O of g. That's the smoothest rule. That's at least the way, this is one possible smoothest rule. So what we have at our disposal is that f is asymptotically non-decreasing and that g is smooth. And we know this is true for certain values of n. In this case, that n is a power of b. So what I'm going to do is I'm going to show you that if you make this presumption about n, and you know that f is big O of g for these values of n, you could just drop all of this, presuming that f is asymptotically non-decreasing and f and g is smooth. And as we previously established, there's many common complexity functions that are in fact smooth. Like we talked about constant functions, log base 2 of n, we talked about n to the power of k. These, for example, are all smooth functions. So meaning that you could use this as a tip or trick to analyze your algorithm's running time in a much simpler manner without having to cut corners. So you're not actually cutting corners. That's the beautiful part about it. You're cutting corners in the best of ways, meaning that you're not losing anything. If your goal is to get a big O statement that it involves all values of n, this smoothest rule will allow you to do that. Is that beautiful? So you don't have to go cutting things in floors and ceilings. You don't have to do all that dirty work. If you want to presume, for example, that n is a power of 2, if f is an asymptotically non-decreasing function and g is smooth, then you're allowed to do that. And it gives you this conclusion at the end. So it's very slick. So you could use this to simplify some of your time complexity analysis if it is actually relevant for what you're doing. So for example, like I said, there's some algorithms like merge sort, binary search, many of them that involve cleaving things into halves. The smoothest rule actually makes the analysis go a little bit smoother. So anyways, let's do the proof now. So I'm going to have some setup for this, and I warn you in advance. There's going to be a lot of variables that are going to be kicking around, but it's not going to be too bad. I'm hoping that I'm going to have some bookkeeping at the beginning that's going to make this work. I'm going to be invoking these definitions to make this possible, okay? So just follow me very carefully. So we know that function f is big O of g, right? We know this. This is given to us when, but we know only when n is a power of b. n is a power, that says power by the way, it looks like power, it's the power of b, okay? It's the power of b. So that means that there has to exist those constants, right? The constants that we get for the big O notation, but it's only for these specific values of n, right? So that's going to play a big role in this proof. So there exist constants C, I'm going to call them C1 and N1, which is positive integer, and N1, which is a positive real number for C1, and N1 is going to be a positive integer, such that for all n greater or equal to n1, where n is a power of b, that's an important bit of this, n is a power of b, then we know that f of n is less than or equal to c1 times g of n. So that's the first thing. And this is true for all n where n is a power of b, but it has to, there are at least n1. So let's talk about where we're going next with this. So now we remember, we know f is asymptotically non-decreasing and we know g is smooth. So we would like to use these facts, okay? Like I said, we're going to have a little bit of bookkeeping, but once we get past the bookkeeping, you're going to see that this is actually going to come out quite smoothly, as I like to jokingly say. So this is actually a really good exercise on understanding why the types of functions actually really do matter. So knowing that a function's increasing, if it's non-decreasing, like these are important details. So when somebody tells you, Dan, all that calculus that we learned, like, Dan, it didn't really matter. Like, say, for example, you took a calculus class, or if you didn't, that's okay. I've gone through most of the things you get and need to know here regardless. But often a common complaint of CS students is that, why do we have to take this calculus class? If you really want to understand the whys of some of these rules that you learn sometimes in your lectures, this is why. It's because some of the reasons why you need to know, like, how a function's increasing, decreasing, etc. These are all important elements to prove statements like the smoothness rule. Because you need to know what a function, like what we're even talking about, right? And calculus gives you an intuition for how that works. But that's just an aside here, okay? So next, function g is smooth, right? So we have two properties we can use. Function g is smooth. But remember, we already proved that it's b smooth, right? Implying g is b smooth. Remember, we proved this. Where we're constants, so we're going to have constants, C2, which is a positive real number, and N2, which is a positive integer, exist. And it has to be that g of bn is less than or equal to C2 times g of n for all n greater or equal to n2. Remember, this is part of the definition of b smooth, right? You might recognize this for, like, when we had smooth, it was just 2 times n. Now it's just bn. Do you see why we might need this b, okay? So this is one of the reasons. So anyways, now we have this. Now we're going to invoke the fact that f and g are both asymptotically non-decreasing. Both f and g are asymptotically non-decreasing, right? And remember, the main reason why we know g is asymptotically non-decreasing is because it's smooth. It's one of the conditions for being smooth. non-decreasing. So that means that there actually has to also exist other constants. There exist 2 points, n3 and n4. I'm going to give them those names. So n3, n4, which are both going to be positive integers, exist such that f of n is less than or equal to f of n plus 1. And g of n is less than or equal to g of n plus 1 for all n greater or equal to 3, sorry, n3, for all n greater or equal to n3, and n greater or equal to n4, respectively. So these are both also going to be important because we need to make sure that we get big enough values for the input so we can ensure that, that we are on that one side where it's always going to be going up or it's going to be plateauing. So we got all the bookkeeping. Now watch this. This is going to be one of the fun examples here where I'm going to pick a really interesting constant for n0. So watch this. Now I must stress that this isn't the most elegant or optimized version of this. But this will certainly cut it. This will cut the mustard, okay? So I'm going to pick n0 as follows. Now I'm going to pick n0 first, which is kind of strange because you're used to me picking c first. But I'm going to pick it this way. The reason why is because we have all of these inequalities, right? All of these inequalities, they all have this property that they need to be for a sufficiently large value for some input. So what I'm going to do is I'm going to pick it so that it is large enough for all of the inequalities to be true. But I'm going to throw b in there as well, just to make sure it's really going to be big enough, okay? Now watch this. Now, this is why I need this to be the case, because I'm going to have a whole bunch of inequalities I can now write out in use when I make n0 this big. So now I'm going to use a property that we have at our disposal relating to the powers of b. So this is another key part of this. Then observe that for any n greater or equal to n0, and I must stress to remember that n0 is greater or equal to 1. So just keep that in mind. There exists integer k. So this is a claim I'm making to you, but I at least hope that it should be clear enough to you where it comes from. There exists integer k greater or equal to 0, such that I'm going to be able to sandwich things like this. Such that b to the power k, so some power of b, is going to be less than or equal to n. But this one has to be sandwiched between this power of b and the next power of b. But this cannot exceed b times n. Why? Well, just think about it. If I have a power of b here, suppose that this was indeed a power of b, then it would be equal. But now, suppose that it actually isn't. It's somewhere in between the two. Now, if it was the case that n was a power of b, say it's b to the k, then b times n would just be b to the k plus 1, right? But we know that the next power of b is definitely going to be bigger than n. Hopefully you see this. So I'm sandwiching it like this deliberately because we are dealing with asymptotically non-decreasing functions, so we can look at their inputs. And we can make statements about if it's smaller or larger or equal at those points. So I'm going to yield this to help this out. So, and we're going to have the following. So you're going to watch this be rather slick. So watch this. So watch this. I'll have to grab that eraser. Let's grab this one. So now this is where all of this is going to come together. It's all going to come together now. I'm giving you no BS here. It's all going to come together now. So we have that we could sandwich n in between different powers of b. And as follows. So watch this. And we know that now we know f of n is less than or equal to f of b of k plus 1. This is because f is asymptotically non-decreasing. This we know. But this right here, remember, this is a power of b here. So remember, this is a power of b. We have something that we could say about powers of b when n is a power of b. Remember, we have the big O claim. C1 times, this has to be less than or equal to C1 times, not F, it's going to be G. This is how we're going to bridge from F to G. C1 times B to the K plus 1. This is because F is big O of G when n is a power of b, or power of b. Remember, we have this. Then next, because of the way I sandwiched the powers of b, notice that b to the k plus 1 is less than or equal to b times n. So I could say this. So C1 times g of bn. So this is because g is asymptotically non-decreasing, right? And we know that b to the k plus 1 is less than or equal to b times n. Now, this has to be less than or equal, because remember, now I know that g is smooth, right? But that means it's b smooth. But look what we got right there. We have g of bn, and we established that that's going to be less than or equal to some constant times g of n, right? So I'm just going to put that in. C1 times C2 times g of n. And this is because g is smooth. And as we established, smooth functions are b smooth. And lastly, I'm just going to put this all together. So I have C1 times C2 times g of n. But what could you pick for C then? Now you have f of n is less than or equal to C1 times C2 times g of n. Well, it's right here. There's C right there. So we're going to just select C is equal to C1 times C2. Therefore, C and N0 have been selected. So just to kind of recap everything, have been selected so that f of n is less than or equal to c times g of n for all n greater or equal to n0. Therefore, we have the definition of big O, right? Therefore, f of n is big O of g of n unconditionally. And we're done. This is unconditionally. It looks like it melted, like somebody put some cheese on top of something that maybe shouldn't have got melted with cheese. That says unconditionally. And that concludes the proof for the smoothness rule. So now we know that the smoothness rule is in fact true. If there are any questions, I'm happy to answer those. But that's how we can prove this. This is one proof for the smoothness rule. Very slick, right? So everybody's having a good time. So I'm going to do one more thing with you here today. But the big thing, like I said, is that you can use the smoothness rule to do all sorts of simplifications to your analyses. So the big thing, of course, is that if you presume n is like a power of 2, the smoothness rule says that as long as f is asymptotically non-decreasing and g is smooth, which most categories of complexity functions, with the exception of things like the exponential functions, they're all smooth. So you're allowed to legally make that assumption. for most cases that you're going to probably run into, at least if you're dealing with the realm of polynomial time algorithms, where you're just going to be able to throw the smoothest rule at it, and you could simplify your analysis so you don't have to worry about cutting, like, oh, does it cut in or out into a half when you're actually doing the analysis of counting the steps. What you could do is you could just straight up say, okay, assume n is a power of 2, then this is how it works. And then you could do the big O for that. If it makes it any easier for you, you could come up with your complexity function, which I would recommend you do this regardless. So you don't even have to presume n is a power of 2. You could just straight up just count up all the operations. And then what you do is in your analysis after that, then you want to prove it's some big O of another thing, or another complexity function. Then you could presume n is a power of 2, simplifies down your complexity function, and then you could proceed from there. It's really a really slick tool. And it's used in all sorts of other interesting algorithm analysis theory. So for example, you may have seen variants of something called the Master's Theorem or the Master Theorem. Some use the smoothness property at its disposal. For example, all 3 cases of the Master Theorem, at least in some restricted versions, not every version of the Master Theorem, but most certainly the ones that are of simpler forms where they make presumptions about the powers of B, such as I have here. In those cases, this property is actually what gets you from presuming n is a power of something to your ultimate conclusion. You could use the Smoothest Rule to do that. It's very interesting, right? So I thought for the last thing we'll do here today, I'm going to revisit the final example I did last time. And I'm going to show you how we can use the Smoothest Rule to greatly simplify what we were doing there. So hopefully that sounds interesting to everybody. So I'm going to erase the boards here, and we're going to do this last example together. And I'm hoping that I'm hoping here that you're going to see that the Smoothest Rule is going to make a lot less work for us for our next example. It's still going to have the same technique that's going to be used, but it most certainly will not be nearly as complicated with its bookkeeping. My goal is to get rid of all of the bookkeeping. I don't want any more bookkeeping where I have to presume power, like I have to round up numbers and make that a variable or anything like that. I don't want any of that. So my goal here is I'm going to use smoothness to eliminate all such bookkeeping. And you're going to see that I'm going to be able to make some simplifying assumptions. You're going to notice that it may even make it easier for us to find C and N0. In fact, they may not even be the same ones because of the way I did my bookkeeping. I mean, they're valid, but most certainly they may not be the same ones. So let's get on that. So let me know in the chat how you doing. Just got this one last example I want to do with you. But yeah, my goal here is to really tell you that the smoothness property is really helpful for you want to simplify your analysis. So I'm going to show you now how we're going to achieve this. So as I said, it's one of the best known but also obvious secrets from algorithm analysis that frankly I think a lot of students never learn. It's sort of just this thing that gets thrown at people and they're like, oh, you can make that assumption? Is that okay? And then, or they just presume, oh, the analysis is easy enough that I can make this assumption, then I can generalize it. Which in the latter case, that is often true, as you're going to see with this example. Because in my previous example, when I did this with the harmonic numbers and logarithmic functions, when I did this, you see that I was able to get around rounding up and down to next powers of 2 that I needed by doing a little bit of bookkeeping by making more variables. You're going to see that using the Smoothest Rule that I could get rid of all of this entirely. So that's why I'm going to show you this. So you're going to see that this is going to have a lot less setup to it. So let's get on this. So we're going to revisit our harmonic number example from last time. So we're visiting harmonic numbers. So last time I had shown you that h of n, the nth harmonic number, which if I want to remind you, the nth harmonic number is equal to the sum from I is equal to 1 to n of 1 over I. So this is just 1 over 1 plus 1/2 plus 1/3 plus all the way up to 1 over n. I'm going to show you that h of n, the nth harmonic number, is in fact big O of log n, specifically log base 2 of n. But even then, that doesn't matter too much for us. Now, you might say, Dan, like we didn't talk so much about what the nth harmonic number, like h works. Like how does h work? So what I'm going to be doing is I'm going to presume that n is a power of 2, but specifically I could do also this. I can observe that the harmonic number, nth harmonic number, if I look at h as a function, I can tell you that h is asymptotically non-decreasing. It's asymptotically non-decreasing because of the following. Because, well, I'm just going to write out the definition again. 1 over I. This is going to be strictly less than the sum from I is equal to 1 to n of 1 over I plus 1 over n plus 1. But notice this is strictly bigger than 0, right? But what's this? What's this? This right here is just simply going to be equal to the sum from I is equal to 1 to n plus 1 of 1 over I. But this is just h of n plus 1. So this is true for all n greater or equal to 1. So that means that n0 in that definition for the asymptotic non-decreasing, you would be just 1. So that means that my finite harmonic series, or the nth harmonic number, if I think of this as function h, it is asymptotically non-decreasing. You can find n0 equal to 1 works. This is because when I add the next component, go to the next entry, notice that it's just going to be adding a positive quantity every single time, meaning that the quantity only makes it bigger, it never gets smaller. So it is asymptotically non-decreasing. So that means that we have, say if we're trying to prove, for example, that h is big O of log base 2 of n, then it has to be that f, which is our nth harmonic number, or h, is asymptotically non-decreasing. Log base 2 of n, we have already proven that that is smooth. So we have all of the conditions necessary to apply the Smoothest Rule. So we're going to prove, again, we're going to try proving this again, but we're going to do it a more refined way. We're going to prove that h is big O of log base 2 of n. But this time, you're going to see I'm not going to need any bookkeeping. It's just going to be rather nice and slick. So you're just going to see I'm just going to purely apply the trick that I used last time. So I'm going to assume n is greater or equal to 1, because that's just the way these definitions work. N is greater or equal to 1 is a power of 2. This is very often how you could set up using the Smoothest Rule. Power of 2. Then here's what you can do. Then h of n is equal to h of 2 to the power of k for some k greater or equal to 0. And we also have the following property, that h of n is equal to the sum from I is equal to 1 to n of 1 over I, which is going to be equal to 1 plus 1 plus 1/2 plus 1/3 plus all the way up to 1 over 2 to the power of k, which this is just going to be simply h of 2 to the power of k. You can see right away, if you see my previous example, how much more slick this is. Because now I notice that I don't have to round up to the next highest power of 2 or anything like that. I just get it. I already am working at a power of 2. So now I'm going to lay out the game plan for the big O proof. So let me just head over here, okay? So we find constants. C, which is a positive real number, and N0, which is a positive integer. So that the following is the case. So that H n is less than or equal to C times log base 2 of n for all n greater or equal to n0. So now I'm going to employ the same trick I used before. So we're going to formulate that second series. So we're going to formulate a second series as follows. So you're going to recognize this from last time. So we're going to do this on the right-hand side. So we're going to do this on the right-hand side. So I'm going to grab terms successively. I'm going to use the same trickery. This common technique you can use when it involves the harmonic series. So 1 is in fact less than or equal to 1. So I'm going to take each one of the terms I have there. I'm going to grab them by increasing powers of 2, the number of terms, and I'm going to bound it by whatever 1 over that power of 2 is. So I'm going to have 1/2 plus 1/3. These are the next 2 terms. This is all going to be less than or equal to 1/2 plus 1/2. Then I grab the next 4 terms, because that's the next power of 2. 1/4 plus 1/5 plus 1/6 plus 1/7. Notice it always goes up to, but not to the next power of 2. This is one nice design about how grouping them like this works. All of these are going to be less than or equal to 1/4. So I have 4 1/4. And you can keep doing this. Keep doing this. For each successive power of 2. So you'll have 1 over 2 to the power of k minus 1 plus 1 over 2 to the power of k minus 1 plus 1 plus all the way up to 1 over 2 to the power of k minus 1. So the next, just before the next power of 2, like before, this is going to be all less than or equal to 1 over 2 to the power of k minus 1. And this is going to be done 2 to the power of k minus 1 times. So this is written this is written 2 to the power of k minus 1 many times. And then I have my last term like before. 1 over 2 to the power of k is less than or equal to 1 over 2 to the power of k. So if you take this, remember everything here is h of n, which is now equal to h of 2 to the power of k. This is the second series which I'm bounding from on the above side. So I'm making everything on this side is going to be bigger or equal to whatever's over here. So I'm going to put that all together over here. So let's do this. So this means that h of n is equal to h of 2 to the power of k, right? We're not needing to do any rounding up, right? We always have it where they're equal like this. So we have 1 plus 1/2 plus 1/2, right? This is the right-hand side of that I formulated over there. So I have 1 plus 2 1/2, which remember this equals 1. Then I have 4 1/4. So if I keep writing out powers of 2, where it's 1 over that given power of 2, when I write it that many times, it's just always going to sum up to 1, right? So this keeps happening, right? And I have 1 plus 2 to the power of k minus 1. I write that 2 to the power of k minus 1 times. This is just going to be sum equal to 1. And then I have the 1 over 2 to the power k again. But remember, as we established last time, when you do this, it's just going to end up being equal to k. Because remember, this is 2 to the power of 0 to the power 1, 2, 3, all the way up to k minus 1. How many of these have I written? How many groups of these? There's k of them. Plus the last term, 1 over 2 to the power k. But now, since I know that h of n is equal to this, I could just proceed as follows. So observe that for all n greater or equal to 1, h of n is less or equal to k plus 1 over 2 to the power of k, which this is equal to, remember, k here. You might say, okay, Dan, what's a k? Well, think about it. Think about it. In our example over here, we wrote out what that was. Well, remember when I wrote out the definition of a logarithm, right? I have 2 to the power 1, log base 2 of 2 to the power of 1 is just 1, right? Okay. Well, we have k. Well, notice that this would be, in fact, whatever log base 2 of n would be. If you're unsure about that, go back to the previous time we tried going through this, and you'll see that I'm just talking about the same thing. And remember, 2 to the power k is equal to n. So I have log base 2 of n, which it's really unclear, just remember what it would be. Remember, we know 2 to the power of k is equal to n. So I'll just draw it off to the side here. So I have n is equal to 2 to the power of k. So if I take logarithms of both sides, meaning I apply it to both sides, because these are equal to each other, so that's their logarithms must be equal if I take them on both sides. This will be log base 2 of n is equal to log base 2 of 2 to the power of k. There's a power law, which I'll be discussing one of the future streams here, or lectures here. You'll end up with a k out front here, then you have log base 2 of 2. This is just 1. So that's where this comes from, if you really just need to derive it yourself. So that's where this comes from. But this is less than or equal to log base 2 of n plus 1, because 1 over n could never exceed 1, because n is greater or equal to 1. So now I have h of n is less than or equal to log base 2 of n plus 1. So I'm going to try using the same trickery I used before, but now I have a much smaller factor here, so I'm going to pick c is equal to 2. So I'm going to play lookalike. Then we need to find n0. We find n0 so that h of n is less or equal to 2 times log base 2 of n. So notice the following. So notice that when n is greater or equal to 2, we know that h of n is less than or equal to log base 2 of n plus 1, which remember we have that from up here. It's right here. Is less than or equal to log base 2. And we're going to use the same trick we used actually earlier on in the session. Log base 2 of n plus log base 2 of n, which this right here has to be greater than or equal to log base 2 of 2, which is equal to 1, right? For a sufficiently large value of n. In particular, it has to be the case when n is greater or equal to 2 because logarithms are increasing functions, right? Which this, in fact, is equal to 2 log base 2 of n, which that's the right-hand side. So we just choose n0 to be equal to 2. Choose n0 is equal to 2. And now what we do is we employ the smoothest rule. So we're going to employ the smoothest rule here. So the function log base 2 of n, remember we established this earlier on, is smooth. So log base 2 of n is smooth. So we're going to use, so this is us invoking the fact that log base 2 of n is smooth, so we're just going to use the smoothest rule here. Therefore, by the definition of big O, H is big O of log base 2 of n unconditionally. And we're done the proof. Now, hello. But yeah, no, so I have given you a much simpler version of the last example that we did last time. So notice that now there's no more bookkeeping. That actually simplifies and smooths out the analysis so we can focus on the fundamental technique here. Is that wonderful? So yeah, no. Now, how are you doing there, OJ? Yeah, no, I just finished going through this trickier example. So today we've been talking about smoothness. So I've been showing how you can make some simplifying assumptions about the inputs of functions so that it makes everything go a lot easier. So you don't have to worry about like rounding up or down things. If you want to presume like n's a power 2, then you can always know that it's always divisible by the number of 2. Which is often handy when you want to analyze algorithms like ones such as things called binary search. There's other ones called like merge sort, quick sort. You can use it for all those. But yeah, no, that's good. But yeah, no, I just finished covering everything I wanted to cover today. So that's pretty much everything I have to say about smoothness. There was actually another example. Actually, one small detail I wanted to bring up. Is that in the notes, I actually do have another way you could characterize smoothness. So if you're curious about that, I have that in the notes. Those are available over on the Patreon. So if you're curious about that, just go check it out over there. I show how you can, for example, presume that n is an even number. So I show you how you can modify the proof of the smoothest rule to get that, which is pretty neat. It's pretty neat. But yeah, no. So, are there any questions or anything like that other than having a good old chat here? But yeah, so we went through actually quite a bit. We've seen actually how we talked about different kinds of functions. We talked about what a smooth function is. We talked about how we can prove a function smooth. We talked about how the smoothest rule, which is in plain English, is pretty much if I show you something is big O of another thing, but I do it under specific or simplified assumptions. I know, right? Because I've been talking about this since like around noon, so I'm basically recapping like almost like 2 to 3 hours of lecture. But yeah, no, but yeah, no, the big thing here is that I'm trying to show you how you can make simplifying assumptions while getting away with still good results. But yeah, no, what I'll be doing next time will be one of two things. So it'll be either that we focus on logarithms, so I prove things involving big O involving logarithms, or we talk about properties of big O. So those are one of the couple different options we might have for the next session that we have here. But yeah, if you're curious, this week I'm planning to do some more game streams, so I'll be probably playing some more Xenoblade Chronicles 2 or potentially Monster Hunter Rise Sunbreak. What else will I be up to? But yeah, no, you may notice on the YouTube channel I have the videos starting to come out, so keep in mind that after the session's over, I do go back and edit all of these videos from the live streams, and I do in fact put them into compact lectures, so they're usually about 40 to 50 minutes long tops. Usually I try to make them shorter, but sometimes it's easier to just have one complete lecture. But yeah, no, so I got a lot of interesting stuff going on right now. So my plan is to try to do these live streams, like where we do where we actually learn stuff together here. And also have the gaming streams too. So it'll be a nice combination and lots of content coming out on the YouTube channel. So it won't be, so for those that have been just vying for educational content from me, so keep in mind, I'm not only going to cover Big O. So my plan is I'm going to have these next couple of sessions, I'm going to kind of spread them out a little bit further. I'm going to have some new ones for Big O Bootcamp, but I'm also going to be coming back to algorithms and data structures. and talk about some fundamentals, things like sorting, searching, some fun data structures like stacks and queues. So like how you can implement a stack or a queue and how they work and what they are. If you're curious about some of these things, like whether it be for just general interest, I try to make it so it's fun for everybody. So these are far more technical topics, but the other ones, such as these, I'm planning to use more props in that. That's what I usually like to do. So I usually like to bring in some fun characters. I already had Miss Kitty here helping me show you how mathematical induction would be used for one of our proofs. But yeah, no. Hopefully you had a little bit of a good time here, even if it's a lot of stuff to take in all at once. But yeah, all the resources for these lectures will be available over on the Patreon. If you have any questions, just let me know. I'm really happy to answer anything. But yeah, no, I think this is the perfect place for me to stop. And I do appreciate everybody coming on down. It was a pleasure to have everybody coming in, hanging on out. And do tell your friends if you're interested in computer science, or maybe you are taking a computer science class, or you want to learn computer science. I'm going to be going through and doing much more series like these. I do already have some series on the YouTube. For example, if you want to learn how to do some basic programming in Java, I've started a series over there. I'm planning to pick up that series and continue it. So far, we're up to a Hello World program over there. So I'm planning to build on that some more. So just check out that on the YouTube channel. So I will be, so if you're curious about like what's programming, what's that about and all that stuff, I have a very basic, like it's meant for people that don't have any programming background. So like, why do you need computer programming? Why can't you just talk to the computer and the computer does it for you? it's like this kind of discussions there. We're at that level and I work my way down. So why do we have programming languages and all that stuff? So I'm planning to go through some more series like that. I'm also going to be doing some series on data structures and algorithms. So some of you may know about my book, Advanced Data Structures, An Introduction to Data Structures and Algorithms. That book, I am planning to work on its second edition, which will include these additional topics, like I mentioned, like stacks and queues. It will include more fundamentals. That'll also accompany a lecture series, just like my first edition did. But personally, I would like to go back and improve upon those lectures because I would like to see some more topics thrown in there. And then I would obviously state that the quality of these videos are significantly better than the original one I had before. Though some people have still reached out to me and they do appreciate the videos from that series as well, as they are. But I would like to polish them up some more. Even though they are there, they're available freely for you to check on out if you're curious about that. Just check out the YouTube channel. But you'll probably agree with me that the setup I have right now is much better, and I'm planning to go through with the second edition. I'm going to put some more refinements in, and I'm going to be adding some more topics in so that you don't have as many preliminaries that I'm going to presume. So for example, if you don't know what an array is or a linked list is or some like basic sorting algorithms, I'm planning to cover those in the second edition so that you could quite literally pick up the whole book and you could walk all the way through, as opposed to it being more of like, oh yeah, if you know first year computer science, you can pick up the book. That's the way the book is written. I'm going to have some more preliminaries. I may add some more code as well, but like I said, these topics don't require code. They're just something that's helpful if you want to actually implement some of these ideas on a computer, like a physical computer. But yeah, no, it's a pleasure to have people hanging on out. I think this is the perfect place for me to stop. I want to say thank you so much for everybody coming on out. It was a pleasure to be telling you all about smoothness. It's always an honor to do that. And if you really liked what you've seen, make sure you tell your friends to come on down. We have ourselves a great time over here. Oh, I gotta take this hat off. Oh, man. So make sure you tell your friends to come hang on out. And if you really want to support the work beyond this, subscribe, follow, tell your friends. I'm sort of like Santa Claus. I know these things sometimes. And so it's always a pleasure to have everybody coming on out. And of course, support accessible, affordable computer science education, which is my main goal here. So this is in contrast, for example, to going to a university, spending thousands upon thousands of dollars. I'm trying to make that much more affordable for people to access that material. So if you just want to learn computer science, I'm trying to make that something available to you at a much more affordable cost. All these lectures, and most of them will be available for free, but the educational materials will be considerably cheaper than the alternatives that do presently exist. So I want to say thank you so much. And of course, check out the Patreon. There's tier rewards on over there. There's also a subscribe star that I have, and I also have some other avenues as well. I'll have that all in the closing video here shortly, okay, everybody? So I want to say thank you very much. And of course, if you like this stuff, tell your friends, okay, everybody? Just please do it for me. I really appreciate it. We have ourselves a good time here. So I'll say thank you so much, and have yourself a beautiful day. I'll see you later.